All right, so because we're in a bit of a crunch today, we're gonna skip the starter question, but do y'all remember how to graph?
Yeah.
Right, so where's our vertex there, just quickly?
8, -1.
Other way, -1 and 8, right? So we'd go left 1 and up 8, and then we would go right 1 and
Down 2.
down 2, and right left and down 4 squared times 2, which is 8. We go down 8, right? Remember, go down 2 squared times 2.
Oh, crap.
You remember that? Okay, so we go right 1 and down 1 squared times 2. Then we go right 2 and down 2 squared times 2. And left 1 down 2.
Makes sense, but I think I might have messed up on the test now.
I hate when it happens.
Okay, at any rate. All right, so as we've said several times in here, every function makes a shape when we graph it. Okay, the shape is a picture of all the points that work in the function. So far, we've studied y equals mx plus b, and that's the graph of a, what's y equals mx plus b? What is that graph?
I know it's slope-intercept.
The slope-intercept form of what? So what is a graph? It's a line, yeah, it's a line. Graph is a line. Don't complicate this. Okay? And we've also studied quadratics. Ax squared plus bx plus c. And that graph is a parabola. Parabola, right? Okay? Now, so this section in this chapter is about another type of function that we call exponential functions. And they are used a great deal in mathematics and in the real world also. Okay, exponential function is of the form f of x or y equals a raised to the x power. Okay. Notice that the function works differently than the others that we've used in the past. Compare how we get x, y pairs for the following functions by plugging in x equals 10. So on the first one, if I plug 10 in, I get 20, right? 2 times 10 is 20. Now in the second one, if I do 10 squared, I get 100. Now in the third one, if I do 2 to the 10th, what do I get? 2, 4, 8, 16, 32, 64, 128, 256, 512, 1,024. Check it. But I'll bet you I'm right.
It was right? So was it?
1,000? Who needs a computer, right? Who needs a calculator? Boom. Just back off. There you go. Okay. So now, notice each one of these functions has a 2 and has an x. But depending on the placement of each, okay, we get obviously radically different answers, right? From 20 up to over 1,000, okay? And that's going to change the shape of the graph and the way they look also, okay? All right, now, we can always use XY tables, of course, but as we've found out, they're not real efficient, right? When we were graphing quadratics last time, we learned our little graphing technique there, put it in vertex form and shift it and move it, and it was a lot quicker, okay? Now, with exponentials, okay, there's also a specific way to graph it. Okay, but we're going to start with a few simple ones, and we're going to start with an XY table, okay, and then kind of get the general shape of these exponential graphs and then go with it, okay? So we're going to start with y equals 3 to the x, okay? And we're going to label 3 key points, and those 3 points, okay, with exponentials, we're going to have x be -1, x be 0, and x be 1. Okay. So if x is -1, what is 3 to the -1 power?
3.
It is 1 over 3, or 1/3, correct. Okay, now if I plug 0 in, what's 3 to the 0 power? It is 1. Anything to the 0 power is 1. And when if x is 1, what is 3 to the first power? 3. Okay. Oh my gosh. Okay, let's plot those points. All right, so we're at -1 and 1/3. It's about, whoa. Got a new tip on this thing, and obviously I got to break it in. We're at 0 and 1, and we're at 1 and 3. So our graph is going to look something like this right here. Okay? And that's an exponential graph, and that's the general form of exponentials. Okay? Depending on the base, so now 3 is called the base, x is called the exponent, okay, and depending on the base, that determines the steepness, if you will, of our exponential, okay. The bigger that number is, the farther away from 1 that number is, the steeper our exponential is going to be. The closer it is to 1, Like if it's 2 or 1.5 or whatever, the flatter that's gonna be, okay? So now let's do 2 to the x. Okay, so again, we've got our xy points, and we're always gonna make our 3 points -1, 0, and 1 right now until we start shifting this. Okay, so if x is -1, what's y? It's 1/2. 2 to the -1 is 1/2. What about 0? 1 and 1, 2, right? So we're at -1 and 1/2. I should have blown this up. 0 and 1, and 1 and 2. So you can see how that doesn't get quite as big, quite as fast, right? It flattens out just a little bit. Okay. So I should have done another one. Okay, so now let's say it's what we do 1/2 to the x. So again, we're going to make our points -1, 0, and 1. So what's 1/2 to the -1? What is it, Emma?
2.
You are correct. It is
That's what
2.
I said, but I whispered it.
Uh-huh.
I said it.
So let's look at that, right? So if I have 1/2 to the -1 power, okay, that's like 1 to the -1 over 2 to the -1. And how do we make those exponents positive? We switch them around, right? So we get 2. Very good, Emma. Okay, so what's 1/2 to the 0 power?
1.
1. What's 1/2 to the first power?
1/2.
1/2. So let's see what this looks like now. So at -1, we're at 2. We're at 0 and 1. Again, we're always seem to go through that point. And we're at 1 and 1/2. So now it looks more like this. So what happened when I made my base a fraction? It flipped it over the y-axis, right? Because if you think about, now let's think about this for a minute. Okay, 2 to the x. Okay, so if I have 2 to the x, or if I have 2 to the -x, okay, that's a y-axis reflection, right? Well, do you see that 1 over 2 to the x and 2 to the -x are the same thing? Okay, so that's why that's a y-axis reflection, okay? 1/2 to the x or 2 to the -x are equivalent expressions. They're the same thing. Because again, 2 to the -x is 1 over 2 to the x. Or you can rewrite that as 1/2 to the x there. Okay. All right. So let's fill out our box here. Okay, again, so an asymptote is a line that the graph approaches and never touches. So if we just look at y equals 2 to the x here, right? Okay, this graph is going to come down here, but it's never ever going to hit 0. Because can y ever be 0? Can I make 2 to some power equal to 0? I can't. No matter how small I make that power, okay, if I do 2 to the -1 billionth power, that's really close to 0, but it's not 0. Okay? So that is called, the x-axis there, or the axis of y equals 0, is called an asymptote. Because it approaches the graph, but it never touches it. Okay? So again, so you can see now, so when a is greater than 0, when our base is greater than 0, if I look to this function from left to right, it's always increasing. It's always getting a little bigger, and then once we get in this part, then it really starts increasing. Okay? And then if we look over here on the right, okay, when a is between 0 and 1, okay, my function is always decreasing. It's always getting smaller and smaller and smaller. And there it's going to approach that it's going to approach the x-axis, but never touch it. Okay? All right, so now, with that in mind, now, instead of making an XY table, okay, if we look at our box here on these other two, we should just be able to crank these out pretty quickly. Okay, let me blow it up just a little bit. Okay, so look at your box. All right, so let's graph 4 to the x. So I'm going to go, x is -1, what's y? 1 over 4. Good. X is 0, what's y? 1. X is 1, what's y? 4. There we go. There's our graph right there. And it has an asymptote at? Oh, an asymptote. Y equals 0. At the x-axis is an asymptote, right? It's never gonna dip down below that x-axis.
Is it always going to cross on?
0 and 1, until we start shifting it, yes. 0, 1 is always a permanent fixture in there. Because anything to the 0 power is 1. Okay? All right, Josh, let's come back to this asymptote here. Can you see how this graph is never going to get to the x-axis?
Yeah.
Right, and so that's called an asymptote.
So are all of them asymptotes so far?
The y equals 0, yeah, the x-axis is an asymptote for all of them. Okay? All right, so now let's do 1/3 to the x. Okay? So x is -1, y is 3. X is 0, y is? X is 1, y is? 1/3. Look at you guys. And notice again, this function is decreasing. And it has an asymptote at y equals 0.
Is it always gonna be 0, 1?
Until we shift it, correct. Now, because we're gonna use our shifting rules like we've done all year, okay? So then that'll change our asymptote as we shift this vertically, all right? But, you know, with the basic forms, that's always our asymptote. Now, okay, so we want to try and graph these again without our XY table, but just know if you need to jot down a quick XY table, do it. Okay, I don't care. You know, the hope is that we get familiar enough with these transformations and stuff that we won't have to, but if you do, it's not a big deal. Go ahead and do it, okay? All right, so now what is that +1 going to do to this graph?
We'll just have to reenact.
That's right, just play it out in your memories, right? You can make it even funnier if you'd like. There you go. All right, so part B. So now if the +1's up top or on the inside, how's that going to shift our graph? To the
Left.
left or right?
Left.
That one goes to the left.
Oh, that was a guess.
Sweet. So instead of -1 and 1/2, now we go to -2 and 1/2. Instead of 0 and 1, we now go to -1 and 1. And instead of 1 and 2, we go to 0 and 2. Now what does that do to our asymptote?
Hey, hold on, can you go over that again?
So I just took all my x values and because I shifted it left 1, correct? So instead of -1, 0 and 1, I go to -2, -1 and 0. I shift all my x values, I subtract 1 from all my x values basically is what I'm doing.
Okay.
Right? Because it shifted to the left 1.
So your asymptote is the same.
Correct. It does not change the asymptote
So
at all.
Two
you go
asymptote.
2 to the -2nd, and then 2 to the -1, and 2 to the 0.
So, I'm sorry, say that again.
So, 2 to the -2, and then 2 to -1, then 2 to the 0. No? Yeah?
Yes,
Yes.
I think that's right.
Because I'll shift it to the left.
Correct.
-2,
Okay, so now part C, wait. Okay, so part C now, how's this going to shift? To the left or right? Left 1 and up 3. So we subtract 1 from our x's and add 3 to our y's. So we go from -1 and 1/2 to -2 and
and
3.5. Right? So we go to -2 and 3.5. Okay, so we go from 0, 1, we go left 1 and up 3. So that's a -1 and 4. And then we're at 1 and 2. And we go left 1 and up 3. And that puts us at 5. And where's our asymptote? At y equals 3.
I think asymptote is a weird word.
Sure.
So much less.
When I was a teenager, yeah, I thought it was. We made all sorts of fun of that word, but you know, I've grown up since then, Gertie. So.
I don't think I ever will.
All right, so now what's this 1/8 going to do? Right, that's like 8 to the -x, correct? So let's think about it. So it's going to take all of our y values. Yeah, if I have 8 to the x, right, it's going to be 8 to the -x. So think about that. So I'm at -1 and and 8. Right, negative 1 and 8. Oops, that's 7.
Close. We can't do 0.
Let's go to 8. 0 and 1, and 1 and 1/8. Yeah. So you can see how, so you can see as your numbers get bigger, how much steeper it gets, okay?
They probably use this for little kids numbers get small.
Well, okay, as that integer, okay, so 1/8, like 1/2 is flatter, 1/8 is steeper, 2 to the x is flatter, 8 to the x is steeper.
Do you bet they use this for
All right, so now what's that negative sign gonna do?
right and down?
Okay, this, I'm sorry, what's this negative sign gonna do? That's gonna flip it over the x-axis, correct? So it just changes, so we're gonna change the sign of our y's, we're gonna add 1 to the x's, and subtract 2 from the y's. Okay, so I'm gonna do, so here's what I'm gonna do, I'm gonna graph the original, and then in one color, and then we're gonna do a couple of transformations in another color so you can see it, see what it does. So our original then, so if it's just 5 to the x, I've got negative 1 and 1/5, 0 and 1, and 1 and 5. So the black one is our original. Now we're gonna go to red. So the red, all I'm gonna do is do this negative sign in red, so I'm just gonna flip it. So now it goes to negative 1 and negative 1/5, 0 and negative 1, and 1 and negative 5. So now it looks like this. That's what that negative sign does. Now with the blue, now we're going to shift it. And how are we going to shift it? Right 1 and down 2. So I go from negative 1 and negative 1/5 to 0 and negative 2 and 1/5. I go from 0, negative 1, I shift it right 1 and down 2, right there, to 1 and negative 3. And then I go from negative 1, negative 5, I shift it right 1 and down 2. And where's my asymptote? Where's my, how did I shift it?
It's negative.
Down 2, so y is negative 2.
You can always just tell by the.
Yeah, your vertical shift is where your asymptote is.
Oh, you always have to have one.
Always, correct.
Yeah.
So there's our final graph right there. So we took the black one, flipped it over. We took the red one, we shifted it right 1 and down 2. And that's our new graph. Yes?
I'm still really confused on how to find it if the exponent is like x minus 1. I can understand the fact you have to go left and right,
Mm-hmm.
but then like.
So then you just add and subtract your x values. Remember, our x values always start at negative 1, 0, and 1. So if I'm going to add 1 to each of those, then I'm going to be at 0, 1, and 2. Those are going to be my 3 new x values. Okay?
So that's what you want to change it if it's like that? So it's
Correct.
not negative? So what?
No. The positive negative doesn't matter. I just shifted, I added 1 to each one of these values right here,
So
right?
you want it to be negative 1. Okay, so that's what I wasn't getting. Sorry.
Sweet.
Then you subtract 2 on the right side. of the-
Correct, on the y's, because we shift it down 2, so you minus 2 from your y's. But we also, that negative sign out front makes our y's negative.
Oh, great.
Okay? Okay, do I need to talk you through that one a little bit more? Okay, let's do. Okay, so here's what we start with then. So our original then, and I should do that in black, is negative 1 and 1/5, 0 and 1, and 1 and 5. Correct? That's where we started with black.
So is it just like the other graphs where once we're done with like -2 and -1, we're just done with them?
Right.
Okay.
Right, okay? Now, so for the red then, all we do is change all the signs of our y values. That's what that negative sign out in front does. So now it becomes negative 1 and negative 1/5, 0 and negative 1, and 1 and negative 5. That's where our red graph came from. Now for the blue graph, okay, we're going to shift it right 1 and down 2. So I'm going to add 1 to my x values and subtract 2 from my y values. So my blue graph is going to be negative 1 plus 1 is 0. 1/5 minus 2 is negative 1 and 4/5 or whatever that is. Oh wait, it's negative 1/5, sorry. I knew that sounded wrong. So that's negative 2 1/5, then that becomes easy. Okay, I go from 0, I add 1 to that, so that gives me 1, and then I go from negative 1 down 2 to negative 3. Okay, then I go from 1, I add 1 to that, it gives me 2, and I go from negative 5 down 2, which gives me negative 7. There are your 3 new points right there. Okay, so like I said, if you need to just jot a quick XY table to see that, do it. I have absolutely zero problem with that. Okay, but eventually, hopefully, you know, we're going to get good enough we can just say, oh, okay, I flip it over, change my Y values, shift it here, add this to my X, shift it there, subtract this from my Y's, I'm done. Okay? Okay, so for the negative X is the same as what? Well, good, 1/4 to the positive X. Okay, so I'm at negative 1 and 4, good. 0 and 1 and, boom. Where's my asymptote? Y equals 0 in this case. Right? Yeah, 0, right? All right, so what's this 3 out front gonna do? So the 3, yeah, so all we're gonna do is times our Y values by 3, once we get them. Okay, so our X values stay the same, so they're negative 1, 0, and 1. All right, so now our Y values then, so instead of 1/2, right, 2 to the negative 1 is 1/2, 3 times 1/2 is 3/2. 0, 2 to the 0 is 1, 1 times 3 is 3, and 1, and 2 times 3 is 6. There you go, there's your points.
Wait, hold on, redo that.
All that 3 does is take your Y values and times them by 3.
Oh, okay.
Any number out in front like that, okay, once you plug X in, just times it by 3, and that'll give you, or times by that number, and that'll give you your new Y values. So I'm at negative 1 and 1 1/2. I'm at 0 and 3, and I'm at 1 and 6. Where's my asymptote? Did I shift it at all?
No.
I didn't, so where's my asymptote? It's 0, Y equals 0, correct. So again, any constant out in front, multiply your Y values by that. That's all you have to do.
1 1/2.
Yeah. Okay, so now, what's that negative 4 going to do? It's going to flip it and stretch it by a factor of 4, right? So in other words, take all your Y's and times them by negative 4. That's all you have to do. Okay? Our X's stay the same, right? Our original X's are negative 1, 0, and 1. Now, our original Y's would be what? If it were just 1/2 to the X. It'd be 2, 1, and 1/2, correct?
Correct.
But now we're just going to times those Y's by
4.
negative 4. So 2 times negative 4 is? Negative 8. 1 times negative 4? Negative 4. 1/2 times negative 4? Negative 2. And there are your points. So I'm at negative 1 and negative 8. I'm at 0 and negative 4. And I'm at 1 and negative 2. And I didn't shift it at all. So where's my asymptote? At Y equals 0. Okay? We all right so far? Okay? Yeah, it takes a little bit of getting used to, but once you do, you're in good shape. Okay, so now e to the x. So negative 1 and 1 over e, 0 and 1, and 1 and e. And remember what e is, approximately?
No. 2.7.
E is roughly 2.7, real roughly. So 1 over 2.7, a little less than 1/2, so negative 1 and a shade under 1/2, 0 and 1, and 1 and 2.7.
Where did this E come from?
Okay, that's when we start talking about remember when we did continuous compounding? Oh, yes, we did. The PERT formula, because that's what it is.
I think that's around the time where I gave up.
Like
not
pi?
to
Do you
Yeah, okay. No, we've talked about E in here before.
Oh, in this class we had?
Yeah, we have. When we did the finance ones, the compounding,
Oh, the project?
the PERT one, you remember the PERT? Well, Matt, I know we do it in 1050, but I'm pretty sure we do it in 1010.
We did.
Right.
Because we had.
Yeah, right, yeah, because A equals PE to the RT. And if you look back in your notes, you can see what E is equal to. E is the limit is, well, anyway, it's kind of over your heads, but anyway, okay. E occurs tons in nature. When you talk about, if you go to science, talk about law of uninhibited growth and decay, that has the number E in it, okay. When you talk about compounding, continuous compounding, that has the number E in it, okay. So anyway, again, E is roughly 2.7. So did everybody hear and understand that? Unless there's a plus or minus on the end, so unless we shift it vertically, your asymptote's always going to be 0. Now, what's your domain going to be of every single one of these? What's your domain? X values. What's your domain?
Isn't it negative infinity to infinity?
It's all real numbers. Your domain will always be, okay, look at that box on the front page, right? Your domain is always from positive to negative infinity, and that's always the case, okay? Now your range, that's going to adjust to your asymptote. It'll adjust with your asymptote, okay? So for example, on part B, what's my range? Again, range is the Y values. Yeah, on B there. From, well, actually from 0 to infinity, because it approaches 0. But 0 is non-inclusive.
On A?
On B.
Blew me away. 0 on infinity.
So what about C? What's my range on C? Where's my asymptote? At 3. So it's from 3 to infinity is my range. Okay, look at part E. Okay, where's my asymptote on E? At -2. So now it's not -2 to infinity though, because it opens down. So it's negative infinity to -2. You always go smallest to biggest. So you were right in your thinking. I want you to say it right though. So it's from negative infinity to -2 on part E. Okay, what about G? What's my range on G? From 0 to infinity, correct. Again, non-inclusive. What about H?
Negative infinity to 0.
Negative infinity to 0, good. And I?
So it can't.
Ask.
So it's always just the number tagged on the end or 0, infinity.
Correct. Well, no. If you flip it over the x-axis, then it's negative infinity to that number. Right? But again, that number is always non-inclusive. Okay, it does not include that number. Make sure that you get that part. Okay? Hopefully we do all of it. All right, so due to excessive whaling prior to the mid-1970s, the humpback whale is considered an endangered species. The worldwide population of humpbacks in P of T in thousands, T years after 1900, can be approximated by blah. How many humpback whales were alive in 1930 and how many in 1960? And then we want to graph it. So, what do I do with 1930? Where am I plugging it in? But do I plug in 1930?
No.
No, what do I plug in?
1930.
I just plug in 30 because it says T years after 1900, right? So 1930 is 30 years after 1900. So P of 30 then is equal to 150 times 0.96 raised to the 30th power. And then what about 1960? So that means P of 60 is 150 times 0.96 to the 60th power. Okay, somebody get a calculator out and crank those out for me, please.
What's the second one say? Wait, why'd you double it?
Because it asked for 1960.
Oh, are you gonna subtract those two?
No, we're just going to graph. So what's 150 times 0.96 to the 30th power? We got 44.0, we'll just go 44. Well, 44.1, how about that? Okay, and remember, that's in thousands, so 44.1 thousand humpback whales. That was in 1930. Now let's do 60. So you know, do the same thing, 150 times 0.96 to the 60th power.
It just keeps going.
Okay. All right, so let's graph it. So again, so there's about 12.9 thousand, or 12,900 humpback whales in 1960. So you can see how the population is declining quickly, right? So in 1930, we had, let's see, 5, 10, 15, 20, 25, 30, 35, 40, 45. Right, so we go 10, 20, 30, 40, 50, 60. So in 30, we're at roughly in there. And at 60, we're at right around there. So you can see how it's coming on down. Now, hopefully, it'll never get to zero. And it actually, they, excuse me, enacted some legislation that made whaling illegal. So the humpback whale is actually on the rise now.
Yay, how did you choose those points?
Well, they told me 30 and 60, right?
That's because
And then I just
they're
plug the numbers in. So the Y value is 44.1 for 30, and then it's 12.9 for 60.
I'm still not understanding, so.
So that's a point, Emma. So I have a point of 30 and 44,000. That's 1 point.
What are your,
Then I have a point of 60 and 12.9 thousand. So each vertical tick mark is 5 years. Each horizontal tick mark is 1,000 whales. Or excuse me, 10,000 whales. So that's how we came up with those 2 points. Well, because that's how it does. I mean, because it's not linear, it's not a straight, we know it's not a straight line, right? Because we know exponentials. Well, so it's 0.96, so it's less than 1, so I know it's going to curve that way to the t power. I know it's an exponential curve, I know what exponentials look like, so I make it curved. And again, in this case, it doesn't matter, you know, that's never going to get to zero, ever, on that model, okay?
So each horizontal tick mark is
10 years, no, yes, 10 years, since 1900. And every vertical tick mark is 5,000, it's 5,000. Okay, does that make a little more sense? Okay.
It doesn't look very intimidating.
Okay, so how do we solve that? X equals 6 to the y. We want to solve that for y, right?
Right, yeah.
I like it.
Yeah, you'd have to y root it. Yeah, okay, see, we're having a problem here, right?
Yeah.
This is going to lead us into our next section, which we call logarithms. Logarithms help us handle this kind of problem. So